Okay.
Okay, so can everyone hear me, first of all? Yes, okay. So, yes, I'm gonna start with a short introduction. So first of all, good evening to everyone present here, and today is the 6th webinar of the Assam Artificial Intelligence Initiative, and I welcome all of you on behalf of the team, the I team, and so a little bit about I. It's an initiative to promote artificial intelligence in Assam and northeast region of the country, and to build an academic network of students, researchers, and all AI enthusiasts to exchange knowledge. And today we are delighted to inform you that this version of the talk series, we have Homanga Bharadhwaj from University of Toronto. And he is an excellent researcher in AI, and he has experience working with Professor Yoshua Bengio from Montreal Institute of Learning Algorithms. And he will be discussing the setup, formulation, and current approaches in robot learning today. And it's the training physical and embodied robots to perform useful tasks by learning from data. And he will also share his experiences gained during several very good internships he has done in different labs all over the world. And Homango is a graduate student researcher in the Department of Computer Science at the University of Toronto, and he's collaborating with UC Berkeley now. And he is also a student researcher at the Vector Institute. He is currently a research scientist intern at NVIDIA Research. And I lied when I said this is a short introduction because he has done so much work and it's not possible to keep it short. And he's with the AI algorithms team in NVIDIA. Not done yet. So previously he has worked under the guidance of Yoshua Bengio and Liam Paul at Montreal Institute of Learning Algorithms. During his summer internship in 2018, Yoshua, Humango, you can correct me if I go wrong anywhere. So his work at MILA, which is the Montreal Institute of Learning Algorithms, focus on the problems of sim-to-real transfer of deep learning-based planning algorithms in robotic navigation. So prior to this, he also did a winter internship in Singapore, National University of Singapore. Yeah. Okay. So in Brian Lim's lab, and his area of research includes reinforcement learning, deep learning, robotics, and human-computer interface. So now I will let Humango take over, and it's all yours, Humango.
Thank you so much for the kind introduction. Let me share my screen. I hope you can see my screen.
Yes.
Okay, cool. Yeah. So I'm currently a research scientist intern at NVIDIA and a student in the University of Toronto. And cool. Yeah. So already I was introduced, but I'll just briefly mention what I've done so far. So I did my Btech in computer science from IIT Kanpur, and I graduated in 2019. And during that time, I also did a research internship at MILA, Montreal. And after graduating, I did a research intern at this company called Preferred Networks in Tokyo, Japan, which focuses on robotics, reinforcement learning, and some fundamental deep learning algorithms. And after that, I joined the University of Toronto. I just received my MSc from there in January 2021 this year. And I'm currently at NVIDIA, and I'll next be at Google Brain. And since I was asked to describe a bit about how my life trajectory evolved, so I have some pictures and things like that. if you have any questions, let me know. So I started my undergrad in IIT Kanpur in 2015, and unlike, I guess, many people, I already knew I wanted to do research, but the question for me was what to research on. So in high school, I was fascinated with physics. So physics seemed like a natural choice for me at the time. And I started out by doing research in quantum physics and also studying it as part of my first year course requirements. And eventually, we did this collaborative project, which is called phase matching in this particular kind of crystal, in order to observe this particular phenomena called spontaneous parametric down conversion. So, if anyone is familiar with quantum entanglement, this was kind of an empirical demonstration of quantum entanglement in a physical crystal. So it involved a bit of optics and a bit of computation, because I had to create a simulator to simulate this, and of course the final experiment. And these were my kind of collaborators in the lab at the time. Most of them are not in IIT Kanpur anymore. And yeah, that is how I started doing research. And after that, my focus sort of shifted, because I discovered that the learning curve in physics is slightly large, and things are not going as at the pace that I wanted. So, and I started getting interested in cognitive science and AI, which I think has been around for quite some time, but has picked up recently in terms of research efforts. And I started that by doing this long-term project called a new tab page recommendation, causes a strong suppression of exploratory web browsing behaviors, where you did a human-computer interaction experiment by analyzing the web browsing behavior of people on the internet, subject to some manipulations in the web pages. So that is how I got sort of interested in computer science. And then I did some work on machine learning, on domain adaptation, and finally on some adversarially learned inference. So I won't go into details of all this, just providing a glimpse of how the trajectory evolved. And after doing some of the work before, I got the opportunity to do an internship in Mila with Joshua Benje. So this is Joshua Benje here, and Liam Paul. So this is Liam Paul here. So Liam Paul is a roboticist, and Joshua Benje, as you all know, is a deep learning pioneer. And my project focused on the intersection of deep learning and robotics, where we designed an algorithm for simulation to real world transfer, where we trained a policy in simulation, and we want to have that policy deployed on a real robot. In this particular case, the real robot was an RC car, a small car, and the simulator was called a Ducky Town simulator, which is an open source simulator. You can play around with it. Yeah, so we trained it in the simulator and we deployed it on the real RC car. And that was a nice demonstration of what we were able to achieve around that time. And here are just some pictures of what Mila used to look like then. It looks different now, but yeah. And then after that, I graduated from IIT Kanpur. So this is a classroom in IIT Kanpur. This is the Mango Orchard. These are my friends. Yeah, and after graduating from IIT Kanpur, I published a paper that from the work I did in Mila the previous year in this conference called ICRA, which is International Conference on Robotics and Automation. This is the largest robotics conference. So it was again in Montreal at the time. So in that conference, I got to meet a lot of robotics researchers and got to see some of the latest development in robotics. So it combines academia and industry and showcases a lot of different things, not just research. So here you can see this robot. It is a spot robot from Boston Dynamics. So they did a demo of this robot in ICRA, which was cool to watch. And then here, the figure on the left here is the Ducky Town challenge, which is the same environment I used for my project as well. So here, this is a simulated, this is a toy environment, and this they call this Ducky Town. So it's a small town where a car needs to navigate across the town, and there are different things around the road. For example, there are some houses, there is some greenery, and so on. And the car gets input the front camera image, and it needs to decide what control action to take at every time step. So it basically needs to navigate the lane. And the only desiderata is that it needs to keep moving without going off the road, because that is something that we don't want the car to do, go off the road. So that is what the aim of this Ducky Town environment is. And they organized a challenge for this environment where people could submit code to their website, and they would evaluate the code on the simulator, train it, do whatever they want, and then send it to them, to the organizers, and the organizers would run that on the real robot and benchmark performance, and the winner would be the one with whose car keeps moving for as long as possible without veering off track. So yeah, that was ICRA in 2019. And after ICRA, I went to Tokyo to do an internship in this company called Preferred Networks. So here are some of my collaborators in the company, and this is some glimpses of Tokyo. So here again, my project was very similar to the previous project, where we analyzed another approach of doing sim to real transfer, uh, where in particular we wanted to do this transfer where the dynamics of the robot kind of changes in the transfer environment. So yeah, I won't go into details of this again, but this is how I kind of got into the field. And after that, I came to Toronto to pursue graduate studies. And in Toronto, I got to do a lot of different kind of projects, which I'll talk about shortly. So yeah, so I started grad school in the Department of Computer Science at the University of Toronto. Yeah, so that was a brief glimpse of how my trajectory evolved, and I guess back to research now. So my research so far has focused on designing safe and efficient learning algorithms for autonomous exploration. So the idea is that when you have a robot and the robot has a camera augmented to it, a front camera, how do we let this robot sort of autonomously explore the environment, do whatever it wants, maybe with some guidance, and learn skills that are useful for what we want it to do later. For example, maybe we want the robot to open a drawer. Maybe we want the robot to clean a particular place of the house. Maybe we want it to cook our meals. So it could be a lot of different things. So how do we let it sort of explore the environment with some guidance, and where the only sensory feedback that it gets from the environment are these images from the camera that is augmented to it? And the second part is, how does it do it in a way that it is safe, so that it doesn't destroy itself or the environment it is interacting with? So we do not want any sort of catastrophic failures to occur during this process of the robot learning to do things. So those are the two key ingredients of my research so far. And just to motivate the problem a bit more, so there are various applications of robotics currently. For example, if you talk of dexterous manipulation, where the robot has to do something interesting by grabbing a certain object or manipulating certain things. So in this figure, the robot maybe needs to push this glass with this spoon. And then you have legged locomotion, where the robot is a quadruped. So quadruped is a robot with four legs. So the quadruped needs to walk or run on the ground. And here the catch is that it should not fall down, because if it falls down, then it might damage itself. And then, of course, you have robot assisted surgery, where you need to do something very precise, maybe with robots that are different from the usual robots that you see. Maybe they don't have any joints, and we call them continuum robots. So, for example, a robot part might need to go inside your mouth and do some sort of stuff, I guess, inside your stomach. So we need very high precision, and we need accuracy in terms of the final outcome. And of course, we need safety, because we don't want any sort of unwanted things to happen inside your body. And then we have autonomous driving, where the car needs to drive on a road. It gets to see the front camera view, and it needs to decide what control input to give at every step of its motion on the road. And of course, it has to be safe. It should not hit people on the road. It should not veer off track, or and it should sort of drive at a comfortable speed, because there will obviously be people sitting in the car. And then you have space robotics, the Mars rovers, which get deployed on terrain that is largely unfamiliar. So how do we train them on Earth so that they are robust to do whatever we want them to do? Maybe move around in Mars and explore Mars, collect data, such that it doesn't kind of fail in that new environment. So these are different applications of robotics, and each application requires some sort of reusable skill learning and some safety guarantees.
You broke my heart.
Turning off the music. So this is Boston Dynamics, and we have already seen a lot of impressive results in robotics so far. So here the robot, it's a biped robot because it has two legs. So it is very difficult to stabilize such a robot because just like a human, and it might fall down. It doesn't have the nice cerebellum that we have that controls muscle coordination. So yeah, so getting this robot to stand and remain stable itself is a very hard problem. And what these guys showed is that you can actually control it to do some very interesting motions, like for example is dancing here. So yeah, many of you might have already seen this kind of robot demonstrations, which are very impressive. So there are two of them, and they're doing something in synchronously, like they're dancing synchronously. And then you have the Spot Mini robot that's doing something interesting again. So yeah, so we have already seen a lot of impressive developments like this. Then the question becomes, so what's missing from the current pipeline and the current industrial deployment? And I argue that that is the learning part, among others. So most of the approaches that we have in industry so far of robotics, they do not involve any sort of learning from data. So they are basically design controllers that control the robot, and there are no sort of hard guarantees that the robot will continue to work when the environment sort of slightly changes. So because there is very less generalization in that case. So this robot learning is the subfield of artificial intelligence at the intersection of machine learning and robotics that uh, learns robot algorithms from data. So if we have data of humans doing something, for example, humans opening a drawer, how can we train a robot to imitate the human by watching videos of human opening the drawer? Or you could also consider more control settings where the human actually holds the robot and moves it around and makes it do certain things. And that is called kinesthetic teaching, where you're actually using the robot to control different things directly. And the robot can use that data to uh, train some sort of algorithm that generalizes to maybe a new drawer that you want to open in a new room, for example. So that is why learning is important, because we want generalization. So efficient generalization is definitely one of the key research questions. And the other research question is safety, because we need to have some sort of guarantees that the robot is doing what it wants. For example, here, when it's pushing the glass and maybe the glass is filled with water, we do not want the glass to topple at all during its pushing movement, because there might be electronics on the table, for example, laptops, which we don't want to get destroyed when the robot is pushing the cup across the table. And here I show a simulated environment that kind of simulates that problem. One of the environments I created where the robot needs to push this red block on the table without the block toppling. So this is sort of a coarse simulation of this, because it's difficult to simulate fluids in computer simulators. So yeah, and I'll talk briefly about some of the robot learning techniques that are used out there. And the main approach from a research point of view is reinforcement learning, where the idea is as follows. We have a robot in a particular state of the environment. So the state of the environment is like a snapshot of how the environment is currently. So in this case, the robot is the thing you see in red. So it's a differential drive car that has two wheels at the rear and one wheel at the front, and it needs to move in order to reach this goal location. So the goal here is the green sort of region. So it needs to move in order to reach the goal. When it reaches the goal, we say that it has succeeded in solving the task. And the environment, so I created the environment, and here the environment has these purple regions, the circular purple regions, which are traps. So the robot has a lifetime of 100 in the environment, and every time it goes into one of the traps, it loses health by one. So the idea is the robot needs to reach the goal without going into the traps. And ideally, we would not want the robot to die. So when the health counter drops from 100 to 0, uh, the robot will say the robot has died, and that is what we want the robot to avoid. So after going to the traps a few times, the robot should sort of learn that it should not go into the traps and avoid going into the traps in the future, such that it still reaches the goal by avoiding these regions. So that is the setup here, and the state is a snapshot of this setup at a particular time frame. And the setup of reinforcement learning is, given a state of the environment, we choose an action. So the action could be chosen, for example, from a policy that is being learned, and I'll talk a bit about what the policy can be. But for the sake of this discussion, you can assume the policy to be just a distribution over actions given states. So given a particular state, it is a probability distribution over all valid actions. For example, the actions can be move left, move right, move forward, or move left with certain velocity x, move forward with certain velocity x, or maybe move at a certain angle. So it could be all sorts of things. It could be discrete or continuous and so on. In this case, it is discrete, and the action is two-dimensional. So one is the forward velocity component and the other is the angle. So this is a two-dimensional action, and the policy is a distribution over this action. So to choose what particular forward velocity to give and what particular angle to turn. It chooses an action from the policy and executes the action in the environment. So after executing the action, the robot moves slightly in a particular direction, and we say that the state of the environment has changed. So the new state is S prime, and the environment gives a reward to the robot. So the reward is a function of the current state and the current action, and that is a property that is defined for the environment. For example, in this particular environment, I have defined the reward to be a function of the distance between the robot and the goal. So when the distance is less, the reward is high. So that is the setup. And after executing the action, it transitions to the next state and it receives the reward from the environment. And the goal of reinforcement learning is to have interactions with the environment, obtain rewards from the environment, and use that to learn the policy pi such that the agent executes actions that lead to higher rewards. And to quantify that, you can actually keep track of the sum of rewards in the entire episode that you have for learning. So the episode terminates when the agent either reaches the goal or the agent dies in one of the traps. And you can train the algorithm to learn a policy pi such that the sum of rewards it receives at every time step is maximized. So that is the setup of reinforcement learning. And here I'm showing a GIF of what the robot is doing. So you can see it sometimes reaches the goals and sometimes it encounters the trap, but doesn't get trapped. So it is doing fairly well in order to reach the goal without getting stuck permanently in one of the traps. So this is a trained policy on this robot. And the way the learning works is you store the tuples of the state, the action, the next state, and the reward in what is called the replay buffer. So this is sort of a memory that the agent has. And you use that replay buffer, the data in there, to update the policy. And there are different algorithms to do that. Most of them are gradient-based algorithms. So you take the gradients of the sum of rewards that you accumulate in your data batch and update the policy based on those gradients using gradient descent. So yeah, so that is how the basic setup of reinforcement learning works. And the policy in general could be any parameterized function, but in deep reinforcement learning, where deep is within quotes, because most reinforcement learning now is deep reinforcement learning. And all that means is that the policy is a deep neural network. So it parameterizes our distribution. Say the policy outputs, it's a neural network that outputs the mean and covariance of a Gaussian. And then we say that the policy distribution is the Gaussian distribution. whose mean and covariance are the outputs of the neural network policy. And yeah, so that was like a very brief summary of what reinforcement learning is and how it can be used to control an embodied agent. In this case, the embodied agent is the differential drive car. And uh, to read more about reinforcement learning, you can look at this book called book by Sutton and Bartow, which is a sort of a classic text in reinforcement learning. And if you don't have that much time to read the book, there are many online video lectures for reinforcement learning, introductory courses from all the top universities in the world. And there are also some excellent blog posts. For example, this is on the blog post by this person, Lillian Wang at OpenAI, which provide very good intuitions and summarizes all the current algorithms for reinforcement learning. So the field as a whole of reinforcement learning is slightly, I guess, a subset of machine learning in some sense, because the optimization problem you solve here is different. But most of the techniques for machine learning algorithms, like doing gradient descent and parameterizing functions as neural networks of different architectures, are sort of inherited. So there is definitely a huge overlap. So if you're familiar with machine learning, then getting familiar with reinforcement learning won't be difficult. So the second sort of technique I wanted to talk about briefly is this technique called imitation learning. So we saw reinforcement learning, where the agent does sort of trial and error learning. It executes an action, it sees the reward, and then it learns a policy that maximizes the reward. But we can also have imitation learning, where we have some sort of expert demonstration. In this case, my friend is demonstrating how to close the drawer. So this is his hand, it's closing the drawer. And we want the robot to learn how to close a drawer based on a video demonstration of this form. So here you can see the robot arm is actually closing the drawer. And this is the trained policy based on data like this of a human closing the drawer. So I won't go into details of this algorithm, but I wanted to just show what imitation learning looks like and how you can train agents with imitation learning. So the demonstrations could be all sorts of things. It could be a video demonstration where it's a video of the human doing it and the robot must directly learn from it. It could also be demonstrations in a low dimensional state space. For example, if you have the exact coordinates of the drawer and you have the exact coordinates of the hand, then you can track the hand as it moves in pushing the drawer. Then you get the exact information in 3D space of the location of the hand and the drawer. And using that information, that state space information, and the action that the human is executing, you can train a policy to basically imitate that using, again, supervised learning. So the setup here is an expert provides some sort of demonstrations or feedback, and that forms the training data. And as you know, in machine learning, once you have the training data, we can do supervised learning. Here it is supervised because we have the data of the agent states at different points in time. So the state of the hand and the drawer in this case, and we have the corresponding action the human executes, and using this, we can train a model to map from states to actions using a neural network. And that is all that is happening here. And that mapping, we'll call that mapping the policy, because it takes in a state and outputs an action. And then you roll out the action in the environment and you get a trajectory. And then you can have some sort of feedback from the expert. So once you have a trajectory, the expert might say whether this is a good or bad trajectory. And you can use that as additional data for training or updating the policy. And note that it need not be exactly this framework. So in some cases, you do not have access to the actions. For example, in this particular paper, you did not have access to what actions the human is executing. We just had a video demonstration. And in those cases, the problem is much harder. So how do we learn just from the video without access to the state information and the actions? So yeah. So that is about imitation learning. And again, to learn about imitation learning, there are very good resources on the internet. And there is a survey paper that I have linked here. And there are also, I guess, imitation learning repositories where people have summarized imitation learning papers. And for learning about implementations for both reinforcement learning and imitation learning, there are frameworks that have the basic algorithms already written out for you, and you can play around with those algorithms in particular control environments. I'll talk about the environments in the very end, but you can play around with those algorithms and see what they do in certain environments using these open source resources for RL frameworks. And note that for most of the implementations, because we are not doing just reinforcement learning, but deep reinforcement learning, so familiarity with the Python libraries like PyTorch or TensorFlow is important, because these are what are used to design the algorithms. Now, that was a summary of robot learning as a whole. And if we talk of the key research questions again, as I mentioned, the first question is efficient generalization. So here the main things are data or environment interactions are costly. So as you know, the real world operates in real time. So when you do something in the real world and collect data, the process of collecting data is costly. So how can we learn efficiently with very less real world data? And related to that is, how do we design good computer simulators that are an accurate reflection of how the real world operates? And that is another research direction which people pursue, designing of computer simulators itself. And well, for generalization, how do we ensure that agents that are trained in a particular setting will achieve good performance in a different setting? So the settings might be different because maybe the dynamics of the robot is different, maybe the environment terrain is different. For example, we have trained an agent to walk, a quadruped to walk on the carpet, maybe in my home, and then we want the agent to walk on the grass outside. So how do we achieve that transfer? And related to the second research question of safety, how can we learn with real robots such that catastrophic failures are avoided? So these are sort of failures which are very harmful for the robot or the environment. Note that some form of failures might be impossible to overcome just because of how learning works, because we have to do some sort of trial and error. But what the key is to avoid catastrophic failures that are extremely bad and that might destroy the system forever. For example, a drone crashing on the ground. And related to safety is the second question of this is called the AI alignment problem, where we have a reward function that incentivizes certain performance. For example, the reward function incentivizes the agent to close a drawer. But how do we ensure the robot learns what we intend it to do? In other words, that the reward function is accurate. How do you ensure that? And the robot doesn't do something else that is sort of potentially more dangerous. So this is really about aligning what the robot does with what we intend it to do. That is again a safety consideration. We'll talk of efficient generalization first. So here are a few GIFs from one of my papers, and to demonstrate what we did here, a quadruped robot is trained to walk. So we incentivize the agent to just walk around in this environment, which is obviously a simulated environment, and the agent just walks around the place. And then we want it to transfer to a task where it doesn't just need to walk around but needs to reach a particular goal. So here the goal is in this red circular region. So how do we transfer from the task of walking to the task of walking in order to reach a goal? So that is what is being demonstrated here. So the trained agent actually learns to sort of reach the goal after we apply our approach. And again, this is another task where the agent is trained on the environment on the left. So here you see all these pillars. The agent needs to reach the goal. So we're training here for the task of reaching the goal, but there are these pillars that are obstructing the agent to reach the goal. And what we want is, we want training in this environment and generalization in this other environment, where the pillars are forming a barrier, and it's more difficult for the agent to reach the goal because it has to navigate the pillars by circumventing them and then reach the goal location. So we want generalization from the environment on the left to the environment on the right. And the key idea of this paper was we need to learn skills that are reusable for different subcomponents of the task. So when the agent learns to walk, it has some skills of what the walking gaits look like. And what we do in this paper is we temporarily compose those skills that the agent learns in a particular environment, such that they will also be useful for the transfer environment, for this environment, because the walking motion is sort of the same, right? It needs to walk in a similar way. So that is how we are able to learn in one environment and transfer to the next environment with very little fine tuning in the target environment. And so when we do this approach of learning reusable skills by composing different skills at the high level, then what you observe is the agent on the right, which is our method that uses this, is able to actually reach the goal. So you see, it's able to reach the goal location by navigating the set of obstacles that form a barrier. But the agent on the left, it is trained with just normal reinforcement learning that doesn't explicitly learn skills that are usable. So in that case, when you do this transfer, the agent just moves all over the place, and in this case, it is inverted, but it doesn't actually get to reach the goal. So through this paper, we sort of demonstrated that to achieve generalization, we need to learn skills that are reusable, that can be used effectively on a transfer environment that is slightly different from the training environment. Now, switching gears to safety, how can we learn with real robots such that we avoid catastrophic failures? Uh, yeah, so for that, I'm sure you might have seen news of Uber self-driving cars crashing into pedestrians, which is obviously an unintended consequence of deploying an algorithm on these cars. So safety is very important for these real-world applications like autonomous driving. And related to the other issue of AI alignment, there was this news about Facebook AI bots that started speaking in a language that is not intelligible to humans. So humans don't understand this language, and that was obviously an unintended consequence of their algorithm being deployed. So this is not a reinforcement learning algorithm, but I just wanted to show how if our incentives that we provide in the form of rewards or supervision are not aligned with what we want it to do, then there can be a potential problem. Uh, yeah. So talking of safety and my paper in particular, the idea here was to do reinforcement learning or imitation learning with constraints, such that the constraints are satisfied throughout training and deployment. So again, we talk of this toy car example where it's the same environment from before, a differential drive car that needs to move to this green goal location while avoiding these purple circular traps. And if we do this normal reinforcement learning, where the agent executes an action, sees where the next state of the environment is, uses the reward and updates its policy, then we observe a lot of failures because we are not constraining the agent to not fail in some sense. We're only incentivizing the agent to reach the goal location without caring about anything. Because as I mentioned, the reward is a function of the distance from the agent's location to the goal location. So that doesn't accurately capture the trap information. So one way to solve this problem would be to encode the fact that you don't want the agent to go into the traps as a definition of the reward function, but that is difficult and it needs to be done differently for different environments. We need to come up with new reward functions. So what we adopted in this paper was a constrained reinforcement learning approach, where we define constraints to be functions from states to this binary set of numbers, to 0 and 1. And the value of the constraint C is 1 when a failure occurs. So when the agent dies in the traps, then the environment says that, look, a failure has occurred. Otherwise, the environment just says that there is no failure currently. So this is sort of a very general feedback we can assume from the environment without any other additional assumptions. And that is the key to defining constraints on what we want. So using this, we can define a constraint on the probability of expected failures. So how probable is the agent likely to fail in expectation? So, and we want to bring the value of that down below a certain threshold. So that is how we define constraints in this reinforcement learning framework. And I actually won't go into details of the algorithm, but just to give a little bit of intuition, we already saw the reinforcement learning pipeline where at a certain state S, the agent chooses an action A from the policy, and then it executes that action in the environment. But we modified the pipeline slightly to have another phase where we learn a value function, which is again a neural network in this case. So the value function based on the constraint keeps track of how unsafe is a current state. So at a particular state S, if you execute a particular action, how likely is it to lead to failure? So that is what this QC function is keeping track of. The probability of failure given you execute a certain action in a certain state. And what you augmented the framework with is at every step we check whether the value of that probability is less than a certain threshold. If it is no, then you resample an action from the policy. And you keep doing this resampling till you find an action in a state such that the probability of failure is less than a threshold. And if that is true, then you execute that action in the environment. Of course, there is an obvious caveat to it that you cannot guarantee that you'll ever find an action that satisfies this. So that is a drawback of the approach and is a limitation. But apart from that, this approach works fairly well. And the additional point I should mention is that in addition to having this safety check, we also train this through constraint optimization, a Lagrangian formulation, whose details I won't go into. But for anyone who's familiar with convex optimization, that is like a standard technique to do learning in the presence of constraints using a Lagrangian. And that is how this QC function is trained in the first place. And we adopt another approach called conservative Q learning to learn this Q function such that it sort of overestimates the probability of failure. So if the probability of failure is suppose X actually, then it estimates a number that is greater than X for unseen states. And we do this because we want to inject the agent with some sort of conservative behavior such that it is very it is very conservative in states that it has not seen. It executes actions only insofar as it won't fail in that particular state. And we call the approach conservative safety critics in light of the fact that the agent learns conservative behaviors. And to give a better intuition of what I mean by conservative behavior, this is the agent during training in simulation. So at the beginning of training, you see that the agent just learns to stand and it's not walking or running. But the reward function incentivizes it to run as fast as possible. But because the approach is conservative, it first learns to stand without falling down. Because falling down is the catastrophic failure here, and then learns to gradually walk slowly and again without falling, and then eventually it learns to run fast as possible without falling. So this is the sort of conservative behavior that emerges if you train the algorithm through our approach. And we see that the failures are sort of minimized or nearly eliminated during the training process. That is important, not just at convergence. And this is some ongoing work. So after training it in simulation, we actually deployed the policy on this real robot, which is a real quadruped, and we see that it doesn't actually fail in the environment, doesn't fall down, as you can see in this video. So which is good, and that is what we want, is the type of behavior that we want from this agent. So to conclude, most of the robot learning techniques that we have so far are still very much limited to research applications. So all the learning-based approaches, reinforcement learning, imitation learning, and so on, they're mainly focused on research, either in industry or in academia. But they don't see widespread industrial deployment yet, due to the reasons of generalization and safety in particular. And most of the robot applications that you see in warehouses or homes for cleaning, etc., they rely on manually designed controllers, which do not learn from data. So this is sort of the classical robotics paradigm that is still dominant in industrial applications that see real world deployment. But what we want is we want to bridge this gap between research and deployment. So there is a lot of scope for research in this robot learning area that bridges this gap essentially, so that we can develop techniques that translate increasingly to large scale industrial deployment, and they become sort of an ubiquitous part of our life. And that is important. We want technologies to become a part of our life. For example, we don't think twice before using a phone, and the mobile phone was not a reality a few decades ago, but now, yeah, no one thinks about a phone, everyone has a phone. Same with computers, and most importantly, same with the internet. And that is how technologies should evolve. And this is a quote by Mark Weiser, who is one of the pioneers of ubiquitous computing. He said that the most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they're indistinguishable from it. So yeah, so that is where I'll conclude with the research part of the talk. But I do have a slide for resources to get started. So from an implementation point of view, so for people who don't have access to large scale GPUs or even CPU machines to do research in deep learning, you can use Google Colab, which is a web resource. So essentially, when you use Colab, what the code you run runs on Google's GPUs and CPUs and not on your local machine. And you can have free access to this, or you can have a subscription for a certain fee and get access to slightly better resources on the cloud again. So this is definitely one of the most important tools now to use if you don't have a physical machine with you. And the second important thing are these PyTorch or TensorFlow libraries that are becoming increasingly popular for deep learning applications, because they let you do this backpropagation efficiently and don't have to write code for backpropagation. And for particularly for robot learning, because real robots like the one I showed you, the quadruped, those are very expensive and difficult to set up. Computer simulators have emerged. I also showed you the simulator for the particular quadruped. So those simulators are very helpful, and they're democratic because anyone can use them. Like Mujoku needs some sort of a license, but you can get it for free if you're doing if you're using it for personal use. But PyBullet is a computer simulator that simulates robots, that is open source completely. And these are very useful for all sorts of robot control tasks. And OpenAI Gym is a framework that builds on the Mujoku simulator, and it provides a very easy interface for accessing Mujoku. And this is very helpful for testing and playing around with reinforcement learning algorithms. And finally, it is surprising how much relevant information you'll discover on the web just by searching effectively. So most of research is about searching effectively on the internet and finding things that you want for a particular application. So I'd encourage everyone to just Google what they want and be surprised at what you find. And if you need more information about how to search effectively, Google has a bunch of articles about how should you insert keywords in the Google search bar so that you get the information that you want. Yeah, I guess with that I'll conclude, and I'll take any questions that are there. Thank you.
Thank you so much, Humanga. And this was really wonderful. And also, really loved your ending um, notes. And so, if anyone wants to ask any question, I think we are open for questions now. And if you want to take some time to formulate your question, I can go over the question that we already have in the chat, and maybe Humanga can um, answer that. So this question is, what do you think about the potential of each reinforcement learning and meta learning in contributing to the making of artificial general intelligence?
Yeah, so that's a very good question, because I think we need reinforcement learning for achieving this general intelligence. And reinforcement learning provides a very convenient theoretical and mathematical framework for framing problems. So the framing of reinforcement learning is such that you can pose any sequential decision making process in this paradigm. So for example, if you want to predict the outcome of certain events, for example, the outcome of the stock market, how that will evolve over time, you can pose it as a reinforcement learning problem. And in fact, a simplification of that called bandit problem, where you just need to choose some actions and the state is sort of constant. So yeah, so I do think that reinforcement learning has a lot of potential in achieving general intelligence, just because of how convenient the framework is and how general it is for framing real world sequential decision making problems mathematically. And for meta learning, I think meta learning is important because it is related to what I talked about, reusable skills or reusable learning. So in meta learning, the idea is you have some sort of a good algorithm that is trained in a meta way, using data from different sort of data sets, and eventually you want that meta trained network or meta trained uh, policy to generalize to different specific environments. And while generalizing, you would use some fine tuning in each particular environment. So, a very common paradigm for meta learning is model agnostic meta learning, MAML, which learns a good initialization of a deep neural network through meta training by training it on different types of data sets. And then during fine tuning, it will adapt the weights of the neural network, which has been initialized through meta training, on these particular smaller data sets that you have for each transfer task. So meta learning is definitely useful for learning behaviors that are useful for a wide set of tasks, and that you can generalize very easily. So the combination of reinforcement learning and meta learning, which is meta reinforcement learning, is actually one of the very prominent techniques currently for learning behaviors for embodied agents that are fairly general and that can be used for all sorts of different environments. Just to give some sort of a concrete example, maybe you want to maybe you have a robot ant with 8 legs, and you want to train a policy on this robot such that even when one leg breaks, maybe now it has 7 legs, one leg just broke off during it's moving around the place, then you want the policy to generalize to that change dynamics as well of the robot, where one leg is missing and the policy should still execute, or maybe 2 legs are missing and the policy should still execute. So in each case, you have a slightly different environment, and through meta reinforcement learning, you can actually train the agent, train the policy such that it would be good for all these different settings. So I do think it has a lot of potential in these situations. Yeah.
Thank you. And Shishir, are you here?
Yes, Pabir, we have one question in
Okay.
live chat. Uh, okay,
Okay. I'm
so
not able to see the
okay, I
question
have
actually.
shared that in WhatsApp.
Okay, I'll just. Oh yes. So the question is from Hriday Shankar Datta, and he's asking. First, he's saying outstanding work, Homanga, and then can you give us some insights into robotic security and safety under different environmental conditions, such as dealing with adversarial vulnerabilities?
So adversarial vulnerabilities are like a topic of machine learning security broadly, I'd say, where like a very I guess classic example now of adversarial sort of security is this example where you have an image, and that image needs to be classified as whether it belongs to a dog, cat, or a panda, or a penguin, and you perturb the input image slightly or maybe a bit more, such that the perturbations do not make the input image imperceptible to the human. So if it's a panda, the perturbations change the image, obviously, but it still looks like a panda to humans. But when the classifier tries to classify it, it outputs the panda as maybe a gibbon or maybe a dog or something like that. That's completely out of what it should predict. And that is, I think, one of the classic examples of adversarial vulnerability, where slight perturbations in the input make the classifier or the machine learning model output something that's totally incorrect. And to deal with that, there are machine learning techniques which have training algorithms for adversarial robustness, where you can also prove that under a certain sort of epsilon perturbations in a pixel space. For example, if each pixel in the input is perturbed by certain epsilon, the output will remain invariant. So if it's an image of a particular class X, the output will still be class X, even when the input pixels are perturbed in this epsilon range. So that is the sort of techniques we have, which are fairly broad, and they provide a proof. For example, a proof by interval bound propagation, where a bound on the pixel space is propagated to the output space, and you can train verifiably robust models through these approaches. And that is a topic in machine learning, but that is not so much of an issue in robotics yet. But that can be an issue, because in real world robotics, for example, a robot moving in the wild with a camera, it doesn't really encounter those sort of situations in a natural setting. But you can think of a malicious adversary that has access to your system and does something funny with your inputs. So in that case, I think the algorithms we have from machine learning would directly translate to to the perception model of robotics, where you take the input image that the car sees and process it. So in that part of the pipeline, you can incorporate those approaches. So I think safety from that point of view has not been explored so much in robotics, but it would sort of translate directly from what we have in machine learning. So the reason it has not been explored so far is because we have other sort of more practically important issues, pressing issues in robotics. For example, the robot walking should not fall down and things like that, which need to be dealt with first before we deal with the adversarial robustness part in robotics. Yeah, that's what I think. Are there any other questions in the chat?
I
Hema?
don't see. Mhm.
Yeah, I have two questions.
Yeah.
Okay. Yeah. So first question is related to that your first question actually, that whatever you discuss about the general intelligence. Okay.
Mm-hmm.
So now, does robot know like why he is doing performing a task? For example, he is pulling a key, or maybe pushing something, or maybe
Mm-hmm.
walking. Does he really know? Because I saw some experiment where people actually did those kind of things, like maybe not now, in future, like
Mm-hmm.
what you can just tell.
So that's a good question. So the question whether robot knows or doesn't know is like a question of consciousness, and the robot obviously doesn't know it, because it's not a conscious agent, in the sense that it doesn't have the same sort of cognitive machinery that we as humans have. So the question, question whether robot knows is, I guess, sort of irrelevant in this case, because obviously the robot doesn't know in the way that we know when you're doing a task. But having said that, the robot does actually know what it is doing, because it has been trained to do that task using a certain reward function. So it would be able to do that task again and again without failing, if if the conditions don't change much. But even when the conditions slightly change, the algorithm might fail. And so that is related to, again, the generalization issue, because our policies that we train are not general in that sense. But from a consciousness point of view, the robot doesn't know. And I don't think our goal is to have robots that know in the same way that humans know. Our goal is to just have robots that can do the things that we want it to do reliably under different sort of conditions. So there's slightly tendential issues, and there is obviously a field of machine learning the cognitively inspired machine learning that tries to bring in ideas from cognitive science into the design of machine learning algorithms. But those are sort of intuitions about how the brain functions and how should we design agents. But that is not the only way in which we can actually achieve this sort of general intelligence. This can also be achieved purely from a computational point of view, where the robot doesn't behave any way that we behave, but it still gets the job done in the way that we want it to do.
Okay, thank you, Homanga. So
Yeah.
I have another question that is this is a non-technical actually. Like,
Mhm.
can you give some idea like about the current status of robot research in India? Maybe it will be helpful for like undergrad or.
Right. Yeah. So, in India, I think there are some groups like in IIT Kanpur. Unfortunately, it is not as developed as machine learning. Unfortunately, so for machine learning, there are lots of different groups in all the IITs and in IISc Bangalore and even Triple IT Hyderabad, where they do fundamental machine learning research and computer vision research. But for robotics, I know that in Triple IT Hyderabad, there is, I think, R. Madhava Krishna's group. I know that because I met many of their alumni in Mila. So, yeah, they do have a very good robotics setup in Triple IT Hyderabad. And I would suggest that to be the go to place if anyone wants to do an internship during undergrad, just to write to the professors in that lab, and maybe also students, because the professors are usually busy. So PhD students in that group in Triple IT Hyderabad. But there are also groups in IIT Kanpur, like there's Lakshmidhar Behra's group in IIT Kanpur in electrical engineering department that does robotics. But I don't know how far of robot learning they do, but definitely very good robotics research. I'm sure I'm missing a lot of places, but yeah, I think that is where robotics research is at India currently. Yeah, not a lot of places compared to other machine learning uh, research.
Thank you, thank you.
Yeah.
So we have a couple, I think two questions.
Yeah.
Pamir, you can, yeah. Hello, Pamir.
Hello.
Oh, sorry. Yeah, I was muted. My bad. Yeah, I'll take these two questions, and I just wanted to ask Humanga if we should limit to like these as the last questions and then close it for questions, or do we
Uh,
still have time?
maybe two more questions. Yeah, that'd be good.
That's good. Okay.
Yeah.
So yeah, I'll make these the last two questions then.
Mhm.
So the first one is by Subrat, and he asks, do you see AI controlling every aspect of robotic system or as an assisting system like for perception?
Yeah, so I think we also need control and not just perception. So the two components of a robotic system are perception and control. So for perception, we have techniques from computer vision that are used for robotics when the input is an image, and we have other techniques when the input is not an image. For example, it could be tactile sensing, where the robot actually has information of touch. It could be auditory input, where the robot has information of sound and environment. So all of these would use techniques from the respective fields in machine learning. But I see a lot of AI in robotics in terms of the control, and that is what I focus on mainly, in a sense, because reinforcement learning and imitation learning are primarily techniques for controlling the robot given a perception input. But obviously, we can't just do control or perception in isolation for robotics. It has to be together, because ultimately we want the perception system to output representations that are good for control. So that is kind of the goal, to bridge both perception and control using AI.
Okay, thank you. I hope Subrat has his question answered. And the last one I'll take is by Vishu, and he asks, can transfer learning be a paradigm used along with reinforcement learning to address noise, volatility? I don't know if it's volatility or tility. Okay, in price indices and stock markets by learning from other markets.
Uh, yeah, so I don't have a good idea of the stock market. I think I just mentioned it at a point. Yeah, I don't know what the state of the art algorithms are for people who do trading in stock markets, but this transfer learning definitely is like a very good sort of approach for settings where you want to use data from an environment or a data set that you don't want to deploy in, but it's just that you have large amounts of data for that particular setting and you want to do something different. So how do you bridge the gap? And for transfer learning, there are approaches like domain adaptation, where you train the perception module, say, of the robot on a particular data set X, and you transfer the representations to another environment through adversarial learning. And that is sort of, I think, one of the popular approaches, adversarial domain adaptation. I'm sure there are other approaches for transfer learning as well, but I don't have a very good idea of what the state is in stock markets. Yeah, sorry about that.
Yes, thank you so much, Homanga. And I think we will end the question session here. And again, thank you so much. And congratulations for all the work that you have done so far. And
Thank you.
best wishes for everything that's ahead. And Sushir, is there anything else that you want to add
No, I think we can
before we?
wrap up. Yeah.
Okay,
So
so we
thank
can
you.
wrap up. Okay, we can wrap up the session here then. Again, I just want to thank everyone, the AI team and Humango, for your time. I know it's all busy schedule right now, and thank you so much.
Thank you for organizing. It
Thank
was
you.
fun. Yeah, thanks a lot. Yeah.
Thank
See you
you.
guys. Bye
See
bye.
you.
Thank you.
Bye.
Thank you.